So in the last couple sections, we were working on measurements, and we talked about the fact that every measurement is inherently an approximation, an estimation, and as such, no measurement could be 100% precise and exact and the number that we're looking for. Well, the follow-up to that then is, okay, if we know that our measurement is not 100% accurate, how off might it possibly be? In other words, is there a amount, a distance away from your measurements which you are guaranteed that it's not further? So if I measure something to be 6 inches, I know that 6 is an approximation, but is there a number on either end of 6 where I'm 100% guaranteed that it's not lower than this or past this? If I can find such numbers, we would call them lower and upper bounds. We are looking for lower and upper bounds, a lower bound and an upper bound. Then we can say it's guaranteed to be between this number and this number. I just don't know precisely where inside that range it is. But what I'm looking for is a lower bound and an upper bound. So today's section on measurements. Let's load this up. And we have the following. So this is section 1.3. And I'm talking, but I don't see me. So where am I? Oh, I'm not important anyways. So section 1.3, measurements, exact or approximate. This is the heading for section 1.3, measurements, exact or approximate. And we start with the following. It says a value is accurate. A value is accurate if it is close to the exact value. Of course, close is relative. What is close for one person might not be close for someone else. But, oh, there we go. Side by side, there we go. Okay. If it is close to the exact value of the quantity being measured. However, in most cases, it is not possible. However, in most cases, it is not possible to obtain the exact value of a measurement. The exact value of a measurement. For example, if I am measuring the distance from the Earth to the Sun, if I'm measuring the mass of an electron, if I am measuring anything, or almost all cases, it is impossible to find the exact value. However, what we want is a range of values that we are guaranteed the true value falls in. So the left and right ends, of an interval in which an exact value of a measurement lies are respectively called the lower bound and the upper bound. Now, the book calls them the lower bound and the upper bound, but just be aware that there are many lower bounds and there are many upper bounds. If I know that my value falls between 6 and 7, 6 is a lower bound, 7 is an upper bound, but 8's another upper bound, and so is 9, and so is 10, and so is 11. Anything above the true value, wherever it is an upper bound. So really what I'm looking for is the best possible lower bound and upper bound. I want to make that interval as small as possible and yet still be certain that it contains the true value. So the lower bound and the upper bounds are half a unit below and above a rounded value of a measurement. A rounded value of a measurement. Thus, the upper bound is calculated as the rounded measurement plus 0.5 units or unit, and the lower bound is found as the rounded measurement minus 0.5 units. What exactly does this mean? Well, it's really best illustrated via as an example. So part A, this is example 4 on page 13, example 4. Jane's weight is 68 kilograms to the nearest kilogram. Determine the upper and lower bounds of her weight. So essentially what we're looking for here is two numbers that would be the bounds of the interval of all the numbers that would round to 68. So what is the lowest number that would round to 68? That would be 67.5. Because anything less than 67.5 rounds down to 67 or even lower. But 67.5 would round up to 68. And what is the biggest number that would round to 68? Well, if you think about it, there is no biggest number that rounds to 68 because 68.5 does not round to 68. 68.5 actually rounds to 69. But 68.4, 68.45, 68.49, 68.4999, all of them round to 68. So I can get infinitely close to 68.5 without ever actually getting to 68.5. So I use a parentheses on that end to indicate 67.5 inclusive all the way to 68.5 exclusive. This is the range of values that would round to 68, which means, of course, we're in kilograms. So the lower bound would be 67.5 kilograms, and the best possible upper bound would be 68.5 kilograms. There is nothing less than 68.5 that we say, okay, up until this point, you round to 68, but past it, you round to a higher number. Because again, I can get infinitely close to 68.5. So in the notation of the above with this 0.5 unit minus 0.5 units, we see that I can write this interval as my rounded measurement plus or minus 0.5 units. Now, since we're rounding to the nearest kilogram, to a nearest 1 unit, it's just 68 plus or minus 0.5, 0.5 ones, 0.5 kilograms. So the range is 68 plus or minus 0.5 kilograms. Part B says, Rushta's height is measured as 155 centimeters to the nearest centimeter. So the measurement is 155 centimeters. Write the interval within which her exact height lies. Following the exact same logic, what's the lowest number that would round to 155? That will be 154.5. What's the highest number? Well, 155.5 doesn't quite, but we can get infinitely close. Units are centimeters. So this is the range of values. I know for a fact that if my rounded measurement is 155, that I am somewhere between 154.5 and 155.5. That is the range. It's the best possible lower and upper bound to include the exact value, whatever it is. I can also write this as 155 plus or minus 0.5 centimeters. So let's do another example. This is now example 5. Majid ran 100 meters in 11.3 seconds. That's fairly fast, I think. His time is measured to the nearest tenth of a second, right? 11.3, nearest tenth of a second. Determine the upper and lower bounds of Majid's running time. So it seems that the 100 meters is completely irrelevant for actually doing the math for this problem. It's just some extra information, but doesn't play a role. We want upper and lower bounds of Majid's running time. Well, what's the lowest number that would round to 11.3? That would be 11.25 seconds. And what is a good upper bound? Well, what's the highest number that bounds those that would round down to 11.3? That will be 11.35 seconds. Hopefully that makes sense. Of course, again, we can write this as 11.3 plus or minus 0.5 of a unit. But what is the unit in this example? We are measuring to the nearest tenth of a second. So the units are 0.1. Therefore, we get 11.3 plus or minus 0.05. The next digits, 11.3 plus or minus 0.05. Let's do one more example. A rectangular garden plot. Ooh, a rectangle. Don't even read anymore. Draw a rectangle. A rectangular garden plot was measured as 172 meters by 64 meters. Determine the lower and upper bounds of its perimeter. Lower and upper bounds of its perimeter. Well, let's think about this. The 172 meters is a estimate. Well, let's do it like this. So the length, I don't know what the length actually is. I measured it to be 172, but I don't know what it is. But what I do know is that 171.5 is less than equal to the length, which is then less than 172.5. And these are, of course, in meters, suppressing the units for the sake of not cluttering the math, but they are in units. The width, which was measured to be 64 meters, I don't know the true value of the width, but I do know that the width is between 63.5 meters and 64.5. Again, notice on the left end, I have less than or equals because I allow it to equal, but on the right, it's strictly less than because I do not allow it to be equal. So what is the perimeter? What's the formula for the perimeter? It's the sum of the four sides. So 2 lengths and 2 widths. So 2 length plus 2 width, or just twice the sum of the length and the width. So for a lower bound, I will take the lowest possible values, which are the 171.5 and the 63.5. Add them together and multiply by 2. This gives me a 470 as the lowest possible value for the perimeter. And as an upper bound, I can do 172.5 plus 64.5 and multiply that by 2. And that gives me 474. So while I have no idea what the true value of the perimeter is, I do know that in meters, it's between 470 and 474. So with those examples under our belt, let's go ahead and jump into exercise 1C. So for exercise 1C, we have the following first question. Find the range of possible values for the following measurements, which were rounded A to the nearest millimeter. So we have 24 millimeters to the nearest millimeter. B to the nearest tenth of a meter. So we have 3.2 meters to the nearest tenth of a meter. And hundredth of a kilogram, 1.75 kilograms, respectively. So again, what are we looking for here? The range of possible values. So we're looking for the range for A, B, and C. So as always, pause the video, try to do it yourself, and then check your answer with mine. So hopefully you did that. 24 is between 23.5 and 24.5 millimeters, of course, parentheses on the right, bracket on the left. 3.2 is between 3.15 bracket and 3.25 parentheses. And C, 1.75 is between 1.745 with a bracket and 1.755 with a parentheses. Again, with the appropriate units of millimeters, meters, and kilograms. Question 2. A triangle. Well, let's draw a triangle. There is a picture in the book, so my triangle is pretty close. Has a base length of 3.1 centimeters and corresponding height 4.2 centimeters. So the height is 4.2 centimeters. Correct to 1 decimal place. Calculate the upper and lower bounds for the area of the triangle as accurately as possible. Well, again, pause the video, try it yourself. Hopefully by now you've done that. Let's go. So the area is 1/2 base times height. Now there are various other formulas for the area of a triangle, but of course, since we're given the base and the height, this is the most appropriate one. What do I use for the base and the height? Well, I can't just plug in 3.1 and 4.2. I don't know if those are the correct values. So let's find a range of values that the base is in. The base is somewhere between 3.05 and 3.15 in centimeters. And the height is somewhere between 4.15 and 4.25, again, in centimeters. So the area, if I use the lower values for those, the area is 1/2 times 3.05 times 4.15. The area is somewhere between 6.32875. And if I use the upper end, 0.5 times 3.15 times 4.25, 6.69375. And these are area units, so that will be square centimeters. The base centimeters, the height centimeters, and while we're at it, let's go back, put in millimeters, meters, and kilograms, so that everything has the appropriate units. Question number 3. With 72 million bicycles, bicycles, correct to the nearest million. So since we're correct to the nearest million, we see that this number here is significant, but the zeros are not. So 72 million bicycles. correct to the nearest million. Japan is at the top of the list of countries with most bicycles per person. On average, Japanese people travel about 2 kilometers by bicycle, correct to the nearest kilometer each day. It's crazy. 2 kilometers per day, correct to the nearest kilometer. So we have one significant figure. Calculate the upper bounds for the total distance traveled by all the bicycles in Japan per day. We just want the upper bounds. So, like before, pause the video, try it yourself. So we need to know the maximum possible bicycles that there might be and the maximum number of kilometers per day that they might be ridden. So the 72 million bicycles, since we're rounding to the nearest million, that would mean an upper bound for the number of bicycles would be 72,499,999. Interestingly enough, in this case, we don't just put in 72.5 million because that would round up. Now you might say, wait a second, I know it rounds up, but you can get infinitely close without ever quite actually getting there. And the answer is actually you can't, because bicycles are discrete. They come in units. So unlike centimeters, where you can have subdivisions as small as you want, with bicycles, you cannot do that. So the actual upper bound for bicycles is 72,499,999. And then we're going to multiply that by, maybe not use brackets since we're using them for bounds. I'll just keep the number, times the maximum for kilometers per day, or the best possible upper bound for kilometers per day, which is 2.5, because 2.4999999, you can still get higher. And if you take these two numbers and you multiply them, 72,499,999 times 2.5, the number is 181,249,997.5. So this is the upper bounds for the maximum number of kilometers ridden in Japan per day. So we have 181,249,997.5 kilometers as my upper bound. And finally, we have question number 4. To determine whether a business is making enough profit, the following formula is used. P is equal to S minus C over S, where P is relative profit, S is sales, and C is costs. You define a formula. You want to know what everything in the formula represents. So P is relative profit, S is the sales, and C is cost. Now, a company has $340,000 worth of sales. So sales is measured to be $340,000. And costs is measured to be $230,000. And these are both correct to two significant figures. So the significant figures here are the 3, the 4, the 2, and the 3. Calculate the maximum and minimum relative profit to the appropriate accuracy. So the appropriate accuracy here is two significant figures. And we want to calculate the minimum and maximum. So here it's actually a little tricky because this formula involves S and C, but you can't just take the smaller S's and the smaller C's for minimum and maximum, because S appears in multiple places and there's a subtraction sign. So to maximize something, you want to subtract as little as possible, and then you're dividing. So it's actually a little bit easier to see if we first algebraically change this into the mathematically equivalent form 1 minus C over S. And in the form 1 minus C over S, we see that to minimize P, that means we want to subtract as much as possible. So we want C over S to be as large as possible. How do you make a fraction big? By making the numerator big and the denominator small, assuming, of course, they're both positive. So to minimize P, we want to maximize C, and we want to minimize S. To maximize P, we want to subtract as little as possible. So we want the numerator to be small, the denominator to be big. So we want to minimize C, and we want to maximize S. Okay, well, what are the bounds for C and S? Well, C is somewhere between 229,000. Actually, let's take a look. This is 230,000, so that'll be 225,000. Anything after 225,000 would round up to 230,000. And what is the highest number for cost? 235,000. Actually, it's 234,999.99, because again, we have the way the monetary system works is you cannot break pennies down into less, or you can't break money down to smaller than a hundredth of a dollar. So less than a cent. So actually the upper bound for cost is $234,999.99. Meanwhile, S is the numbers that would round to 340,000. That is 335,000 would round up to 340,000, and 344,999.99 for the same logic as before. And these are, of course, both in dollars. So P, the relative profit. Let's find the minimum. Well, to minimize P, it's going to be 1 minus the biggest possible C, which is 234,999.99, divided by the smallest possible S, which is 335,000. And this gives me P is within 0.2985 ... And then what's the maximum? 1 minus the smallest C, which is 225,000, divided by the biggest S, which is 344,999.99. And this takes me to 0.3478 ... which means this is P is somewhere into two significant figures, 0.30 to 0.35. So hopefully that made sense. Now let's continue. So we're still in section 1.3, but now we're in the next portion, which talks about the following. And this is very important because a lot of people think that when you're off of your measurement by a given amount, that describes how nice your measurement was. Well, let's think of the following example. Suppose I measure the length of this pencil. Now this pencil seems to be roughly 1, 2, 3, I don't know, 5, 6 inches. Let's see, I measure this to be 7 inches. So I'm off by maybe an inch or two. Well, when the thing that you're measuring is only 5 or 6 inches long and you're off by an inch or two, that's a pretty bad measurement. That's a significant portion of the size of the object that you're off. And if I measure the distance from the sun to the earth and I'm off by a couple inches, that's an astoundingly amazing measurement, even though I'm off by the same amount, because compared to the 93 million miles, which is the distance from the earth to the sun, that's a pretty incredible error or tiny error in comparison. So what we have here is the following. we have two different definitions. First, since measurements are approximate, there is always error in the measurement results. There is always error. A measurement error is the difference between the exact value VE, exact value, and the approximate value, which is VA. In other words, i.e., the measurement error is the approximate value minus the exact value. And you'll notice that it could be positive or negative, depending on if your measurement is above or below the exact value. However, it's not just the error that matters, but it's the error relative to the object that you're measuring. So to that end, we have something called the percentage error. The percentage error is defined as the measurement error, VA minus VE, divided by the exact value. And if we don't care, and we usually don't, whether it's positive or negative, but rather only how far off it is, we will put this in absolute values. And then we want it as a percent. So we multiply by 100 over 100, we multiply by 100%. All that does is it move the decimal place 2 units and adds a percent symbol. So you have mathematically the same value, but rather than as a decimal, you're writing it as a percent. So this is the percentage error. Let's quickly do an example just to illustrate. So suppose that the approximation 22 over 7 is used for pi. Suppose we use 22 over 7 for pi. A, how close, in other words, to how many decimal places does 22 over 7 approximate pi? So pi is approximately 3.14159 I used to know it, 2563, let's see, 2654, 14159 2654. And 22 over 7 is approximately 3.142857143. Well, actually, with approximation symbols, I don't need these. These are approximations anyways. So A, how close to how many decimal places does 22 over 7 approximate pi? And the answer is they're exact to 2 decimal places. So they are exact to 2 decimal places. That's not bad. Not horrible. B, find the percentage error of this approximation, giving your answer to 2 decimal places. Well, in that case, we do 22 over 7, which we just did, minus pi. We divide that by pi. We multiply it by 100%. And my calculator gives me, for a percent error, this is VA minus, let's put it in here. So we have 22 over 7 minus pi all over pi in absolute values times 100%. And it's approximately equal to 0.0402499%. And we want it to 2 decimal places, so 0.04%. 0.04% is not just 0.04. 0.04%. So that's very, very accurate. Another example, we have the following. It says calculate the density of a cube of sugar. So here's a sugar cube. And we are looking for the density. We know that it weighs 2.45 grams. Well, the scientist in me says not exactly. It has a mass of 2.45 grams. It does not weigh 2.45 grams, but it has a mass of 2.45 grams. And we're given the length of a side is 1.2 centimeters, correct to 1 decimal place. That would be the length, not the mass. And it wants us to calculate the density. Now, density is mass over volume, usually given by the Greek letter rho, mass over volume. We have the mass, which is wonderful. That means all we need is the volume. No problem, because in our formula booklet, we have the volume of a cube, length times width times height. In this case, all three of them are 1.2. So the volume is equal to 1.2 cubed when I suppress the units. If I don't suppress the unit, cubic centimeters. On my calculator, 1.2 to the third power is 1.728 cubic centimeters. And then I calculate the density. So density is 2.45 over 1.728. This will be in grams per cubic centimeter. So 2.45 divided by 1.728 gives me approximately 1.4178 grams per cubic centimeter. That's if I keep the 2.45 and the 1.2, and I assume that those are the true values. Of course, what do I do now? I'm going to round to 1 decimal place, and that gives me 1.4 grams per cubic centimeter. But what if, just what if I said, wait a second, the volume is 1.728 cubic centimeters, but I'm going to round that right away in the middle to 1.7 cubic centimeters. If I do that, oh, and don't forget, the mass, which is 2.45 grams, that's to 1 decimal place, 2.5 grams. Well, what density do I get now? I get 2.5 over 1.7, and of course, grams per cubic centimeter. And then my calculator gives me 1.47058 ... grams per cubic centimeter. And that would then give me to 1 decimal point 1.5 grams per cubic centimeter. So this is a different answer. It's close, true, but it's a different answer. And because it's a different answer, this demonstrates the bad part of rounding during intermediate steps. We do not like this. You keep all of your decimal places until the very end of the problem, and only then do your rounding. You will get a more accurate answer that way than if you do intermediate rounding. And on the IB exam, they expect only rounding at the end. You keep all decimals on your calculator to the very, very, very last step. So to that end, let's now enter exercise 1D. Exercise 1D, question number 1. Find the percentage error if we use 3.14 instead of pi. So the exact value is pi. The approximate value is 3.14. The question is, what is the percent error? As always, pause the video. Try to do it on your own. You could always go back to an earlier section or check your notes for formulas. Assuming you've done that, we know the percentage error is going to be the absolute value of your approximate value minus the true value divided by the true value times 100%. 3.14 minus pi divided by pi. Oh, that's negative, so make the absolute value, make it positive, multiply it by 100%, and we get 0.050695 which we will round, unless we're told otherwise, to 3 decimal places, sorry, to 3 significant figures, so 0.507%. Remember, leading zeros are not significant, so the 3 significant figures are the hundredths, thousandths, and 10,000ths place. Question 2. In 1856, Andrew Waugh, W-A-U-G-H, no idea how to pronounce that, announced Mount Everest to be 8,840 meters high. He gave an approximate value of 8,840 meters. After several years of calculations based on observations made by the Great Trigonometric Survey, more recent surveys confirmed the height. So now we have an exact value, or at least an exacter value. I know, not correct English, but I like it anyways, of 8,848 meters. Calculate the percentage error made in the earlier survey. Again, pause the video. Hopefully you've done that. Percentage error is the absolute value of the approximate minus the exact. In this case, it's not really exact because we don't know that's correct either, but it's the most known, and therefore we'll take it to be the exact, times 100%. When I do the math, I get 8,840 minus 8,848 divided by 8,848 times 100%. Get rid of the negative sign. And we have to 3 significant figures, 0.0904%. Question 3. Eratosthenes estimated the circumference of the Earth as 250,000 stadia, the length of an athletic stadium. If we assume he used the most common length of stadia of his time, his estimate of the circumference of the Earth would be 46,620 kilometers. Currently, the accepted average circumference of the Earth is 40,030.2 kilometers. Find the percentage error of Eratosthenes' estimate, whatever, of the circumference of the Earth. So again, pause the video. We get percentage error equals 46,620 minus 40,030.2 over 40,030.2 absolute value. Ran out of room, but luckily I have some cool tools at my disposal here. Times 100%. So when I do my calculator, 46,620 minus 40030.2 divided by 40030.2 times 100, and we get approximately 16.5%. Not quite as nice as the other ones, but not too shabby. And finally, we have the last question in section 1D, which is question number 4. The temperature today in Chicago is 50 degrees Fahrenheit. We have 50-degree Fahrenheit temperature. Instead of using and we'll assume this is exact. Instead of using the standard convention, the standard conversion formula, where degrees of Celsius is 5/9 times the degrees in Fahrenheit minus 32, Tommaso uses his grandmother's rule, which is easier, but gives an approximate value. Subtract 32 from the value in degrees Fahrenheit, looks very similar so far, and multiply the result by 0.5. 0.5, 5/10 versus 5/9 is going to be a little off. So this is exact, and this is approximate. A, Calculate the actual and an approximate temperature in degrees Celsius using the standard formula and his grandmother's rule. Well, 50 minus 32, 18 times 5/9. So the actual would be 10 degrees Celsius. And the approximate would be 18 times 0.5 would be 9 degrees Celsius. Not too bad, whole degree off. B, calculate the percentage error. That's going to be his 9 minus 10 over 10 times 100%, which is approximately 9 minus 10 is 1, negative 1, absolute value is 1, 1 over 10 is 0.1, 0.1 times 100% is, and that would be 10%. I guess to 3 significant figures, it should be 10.0%. The book just gives 10%. So we'll go with 10%. So close enough, I guess. So that takes us to the end of section 1.3. Hopefully it all made sense. If not, you can always rewatch the video. You can also leave a comment below if you have any specific questions. And I will hopefully see you soon in section 1.4. Bye.